Welcome to Monochemistry. Today we're going to continue our discussion about kinetics, and we're going to look at the integrated rate laws. We've already discussed the differential rate laws, and we've looked at how to come up with the rate law expressions for various experimental procedures. In this lesson, we're going to learn a little bit about how to calculate various aspects of either concentration, rate constants, or the amount of time it takes for a reaction based on what we already know about a particular reaction. So let's get started. The first type of reaction we're going to look at is called a first order reaction. And this is exactly what we've talked about before. Let's pretend we have some sort of reaction where element A or compound A is being broken down into some sort of products. Okay? And let's assume that that particular reaction is first order. So the rate law would be equal to, rate is equal to K times the concentration of A, and of course that would be raised to the first power. Okay, so you get the idea. So we know this is first order. Okay, but we know it's first order, but how can we use the information we have then to calculate the concentration of A, or to calculate the rate, or to calculate the rate constant? That's what this equation down here does for us. Let's talk a little bit about that equation. I'm just going to back up a little bit here. Alright, so in first order reactions, a graph of concentration of A versus time in seconds would look something like this. So as you can see, it's not a linear progression. It's a what we call an exponential, in this case regression, because it's decreasing over time. And in order to calculate the slope of that line, or the K value of that line, we'd have to use calculus. We don't want to do that. So what we've done is we've done all the work already. We've come up with an equation here that allows us to convert that data so that our graph would actually look like this. And we can calculate the slope of a straight line. We have our general equation, y equals mx plus b, and that's what this equation here mimics. Okay? So let's talk a little bit about this equation. And this equation is on your data sheet, so you don't have to memorize it. Alright, so we have the concentration of A, and you see that? You have the rate constant, which is K, and you have time, which is T. Time always, always, always has to be in seconds. Now, you notice there's a little T here and a little 0 here. Okay? So what does that mean? Well, at time equals 0, we would have the concentration. That's the value that goes in here. That's why there's a 0 there. T is whatever other time of the reaction you're looking for. It could be the middle of the reaction, the end of the reaction, whatever the time is in seconds, whatever the concentration is at that particular time, that's the value that you'd put in there. Okay, so it's always your kind of later on value minus your start value. And that's how the equation works. Let's try a question and see if we can't figure out how to use this. This is a sample problem. It's on page 571 of your textbook. Alright, so in this particular question, and I've only written the first part of it, there's an A, B, and C part. We're only going to do part A. The sample problem 13.4, you see it here. Now for A, it says if the initial concentration of the cyclopropane is 0.25 molar, what is the concentration after 8.8 minutes? Okay, so we know the initial concentration, or in other words, we know the A naught is equal to 0.25. We know the K was given right here, that's K. We know that the T is 8.8 minutes. But remember, it has to be in seconds, so you would convert that to seconds. How would you do that? You'd use a conversion factor. You'd know that there's 60 seconds in 1 minute, and you convert it. So when you do that, you get 528 seconds. Okay, let's talk a little bit about what this is. This equation represents the natural log. That's what ln. It's called ln, and most of you probably haven't used that before, but that's okay. On your calculators, you should find it. It's usually right next to or underneath log, okay, and it's ln, little l, little n, ln. Okay, and it's a natural log. It works much the same way as a log. Okay, so it's a different type of scale. It's a natural log. And you'll learn more about it in math class. I'm not going to get into the ins and outs of it here, but we do need to use it in this equation. Okay, so it works very much like a log. So now all we have to do, in the question for A, is we know this value, we know this, we know this. All we have to do now is calculate this value here. Okay, so we're going to rearrange the equation, and what we end up with, after we do a little bit of computations here, we end up with the ln of the concentration of A at time t equals negative 1.74. Okay, that's what we end up with eventually. Now, I'm just going to get out my eraser here for a sec. Create some space so that I can do the answer. Alright, that should be good enough. Get my pen back out. Okay, so now what I'm going to do is I'm going to show you how to do this. Now, remember in the pH, the inverse of the log was 10 to the x. Well, the inverse of ln is e to the x. Okay? And if you look on your calculator, you should see that, e to the x. It should be right above the ln button. I want you to find that and make sure you know where it is. So we have e to the x. Okay, so if we were going to do this, in order to solve for the concentration of A at time t, we'd then have to take e raised to the negative 1.74. Okay, so I want you to try that in your calculator. Make sure you can get the correct answer, which is 0.18 molar. That's the concentration of the cyclopropane after 8.5 minutes or 528 seconds of the reaction. Okay, so that's how we solve first order problems. Let's look at the second order. Okay, so second order problems would be much the same, but we'd have some sort of reactant turning into products. Don't mind my messy, I'm doing it fast here, trying to get through this video in under 10 minutes. That's my goal. Alright, so, but in this case, the rate would be equal to some K value times the concentration of A, and of course that would be squared, okay, because it's a second order reaction. Okay, so down here we have an equation that allows us to solve. So if we know that it's a second order reaction, then this is how we would solve the question. And we can solve for, look at what we can solve for. We can solve for the initial concentration if we know one of the other things. We can solve for K. We can solve for how much time has passed. We can solve for the concentration at a particular time. All of those things we can solve for if we know that it's a second order reaction. Okay, I'm not going to dwell on this much longer. This is just straightforward computations. Once you know the values, there's a sample problem in your textbook that you can easily look at, and I would recommend trying it to make sure you can do it. Okay, let's move on. Finally, we have something called the reaction half-life. Now, a half-life is the time required for the concentration of the reactant to decrease to half of its original value. Now, this equation here is specifically the half-life equation that you see in your textbook for first-order reactions. Okay? That's all it is. Okay? The half-life equation is useful because it gives us an estimate of how big the rate constant is. It may not seem very useful in most of the ones we're going to do because we're looking at very fast reactions. But if we're looking at very slow reactions, the half-life becomes very important. If we're looking at reactions that take years, thousands of years, millions of years, then this equation is very useful because we can predict how long something's going to take, or we can predict the reaction rate of that particular reaction. It's not very useful, or not as useful, for quick reactions. Okay, so that in a nutshell are the integrated rate laws. If you have any questions, bring them to class. We're going to try some things with these in class, so you'll get some practice.